We'll talk about work as well. One of the things that's really important to note about work and energy is these are part of this like very deeply obnoxious thing that physicists do, where they will take a set of words that has meaning in English and they will assign to them a totally different meaning in physics. So I am truly sorry, everyone who's going to have to completely relearn what work means and what energy means in a different context. So I'm going to start today out by having y'all just do a little bit of a conversation amongst yourselves about what you think of when you think about energy, so that we can then talk about what this actually means in physics. A note for today, there are going to be a number of moments when I'm going to need you to sort of shift your attention from having conversations amongst yourselves to quickly turning your attention forwards. So just be on the lookout for those cues that I give you to say, hey, now we're focusing back towards me. So at your table groups, I want you to discuss amongst yourselves, what do you think of when you hear the word energy? What do you think that means? Where do we see energy in our daily lives? What does energy mean to you? So go ahead and talk amongst yourselves for a few minutes.
Please don't say that anymore. Don't say that ever again.
Attention back forward. So shift your attention back to me. Asa, please don't.
Asa, focus.
All right. So when you hear the word energy, what does that make you think of? Yeah, Barrett.
Power drinks or energy drinks.
All right. So power drinks or energy drinks. So this is very much an example of what we talk about when we say like energy in colloquial English, which is separate from energy in physics. In colloquial, in like regular English, energy drinks are drinks that have huge amounts of caffeine in them. Caffeine is a drug that happens to make you feel really alert, and so that's like alertness is what is being talked about in energy drinks. Although energy drinks also contain something else that is very good for your energy in the physics sense, which is sugar.
Magnesium.
Sugar is going to be what I'm going to go through here, because sugar is actually a way of storing energy. Because you need energy to run your daily lives, right? Every time you run, jump, play, go play basketball, have discussions about horses, all of this requires energy. And you get your energy from where?
Sugar.
Being introverted.
Food.
From sugar. Again, getting your energy from being introverted is a great example of that difference between energy in English and energy in physics. In physics, we don't get our energy from being introverted, although in English we absolutely do. So, when we talk about how you get energy, you get your energy from your food. Food and fuel can be thought of as stores of energy. They're literally chemicals that, because of how the atoms and molecules are arranged, store energy. And under the right circumstances, that energy can be released. So when you burn calories, that's not a metaphor, it's not a euphemism, that's literally what your body does. You set that sugar on fire inside of you and it gives you energy. In the same way that if you set, a log of wood on fire, it burns and it releases energy. In both those cases, whether it is, a piece of firewood or a candy bar. All right, remind me where I was before the thing started going up.
Burning calories.
All right, burning calories. So, when you have a piece of food, whether it is a candy bar or whether it is a piece of firewood, we literally set it on fire and we release the stored energy inside. So this is an example of stored energy. And in physics, we have a special word for stored energy. We refer to it as potential energy. So this is one of our first types of energy, potential energy or stored energy. And there are going to be 4 different types of potential energy that we're going to talk about. So potential energy is just stored energy. We're going to talk about 4 different kinds of stored energy today. But the first of these is chemical potential energy. This is energy stored in molecules. So anytime you have food or fuel, I'm going to skip this over. food and fuel are both examples of chemical potential energy. All right, what else did you think of when you heard the word energy? Kenji?
I thought of like a horsey running. Energy.
All right, so a horsey is first of all, it's a big object. We got a lot of mass there, and horses run fast. They got a lot of velocity. When you have something that is in motion, when you have matter in motion, it has energy. Anytime there is matter in motion, and a horsey is a beautiful, elegant example of matter in motion. I think we can all agree with that. The internet's going to be very perplexed about why horses keep coming up. They'll just have to wonder. Some student next year is going to be like, what the hell is going on here? Anytime you have matter in motion, we call that kinetic energy. This is the energy of motion. Whenever you have something that's moving, it has kinetic energy. The bigger that object is, the more kinetic energy it has, and the faster that object is, the more kinetic energy it has. Although of those two things, velocity matters way more. Right? It makes a much bigger difference for how much energy there is than just mass. So the thing that really gives a horsey all that kinetic energy is that it goes fast, not just that it's big, right? A cow is also big. It doesn't have nearly the level of kinetic energy that a horse does.
It really is big.
All right, so we have potential energy, we have kinetic energy. What other things do you think of when you think of energy?
Motion. Is that energy?
Sorry, I couldn't hear you. Did you say a sandwich?
No, never mind.
No, say it.
Isn't static energy?
Oh! So when we talk about like static electricity, you have a transfer of electrical current. You've got electrons moving from one thing to another. And if you have electrons that are moving, we specifically call that, even though they're in motion, we have like a more specific term. We call that electrical energy, or electricity. So electricity is just a flow of electrons. And usually that'll be a flow of electrons through some sort of conductive material like a wire or something. You can sometimes have it without wires, like when you get static electricity or like little static shocks and things. This is a form of energy. It's a really useful form of energy. Because the awesome thing about electricity is we can transport it long distance through wires. So you can have like a power plant in one place and then wires that are set up to carry electricity all over. Electricity is really flexible. It's really easy to turn electricity into all kinds of other things. There's loads of other forms of energy that we can turn electricity into. And so this is like one of the, foundational technologies of our society, the ability to take electricity and turn it into other energies, and also to take other energies and turn them into electricity. To generate electricity is a really important, technology that we have. What are some of the things we might turn electricity into? Asa?
Heat.
Heat, absolutely. Heat is a form of energy. Technically speaking, heat is actually kind of a subtype of kinetic energy. Because what heat really is if you imagine, we've got all the air in this room. The difference between the air in this room, if it is 60 degrees, and the air in this room, if it's 70 degrees, is literally that the particles are moving faster. Right? When it's hot, whether you have hot water or hot air or anything else, it's literally just that the individual particles are moving faster. Yeah, this room's haunted. Don't worry about it. It's fine.
Okay. That is actually.
All right. So heat it's like kinetic energy at the super small scale, right? It's the kinetic energy of tiny particles. But really, it's perfectly fine for y'all to think about this, in your normal colloquial way of talking about heat, the same way you talk about heat in regular English as opposed to physics English.
How's that not scary?
You know.
What about air conditioning?
It is a person.
All right, air conditioning is really interesting. So air conditioning, it's literally just moving heat around. What are some other things we can turn electricity into? Yes.
Wi-Fi?
Wi-Fi! All right, so here's the thing about Wi-Fi. technically speaking, Wi-Fi is a color of light.
Huh, what?
Yeah. So light or electromagnetic waves is a form of energy. Now you have some like complex biological sensors that can see certain colors of light. So you can see like red, orange, yellow, green, blue, indigo, violet, like that part of the spectrum.
You can't see Wi-Fi.
Right? There's other animals, like dogs can't see all the same colors that you can. There are animals that can see colors that you can't see at all. Like mantis shrimps have way more sensors in their eyes. They can see way more colors than you can. And then there's lots of other colors that can't be seen by other creatures. A lot of birds can see into the ultraviolet, which is pretty cool. A lot of bees can see in ultraviolet. A lot of white flowers actually have patterns in them on colors that you can't see, but that bees can, or that pollinating birds can. And Wi-Fi, along with microwaves, radio waves, X-rays, those are all colors of light that humans cannot see. But that is something you can turn electricity into, and it is a form of energy. So light is a form of energy. All right, let's talk about what energy is. And then we'll get into why some of these things are going to be, what the missing forms of shared energy are. Technically speaking, this is going to be a very frustrating definition I'm about to give you because you don't know what one of the words in this definition means yet, so I apologize for this. But the definition for energy is that energy is the capacity to do work.
To do what?
To do work.
Energy is the capacity, the ability to do work. So energy is the capacity to do work. So yeah, what's work? All right, this is frustrating because we all know what work means in like normal everyday English, and that's not at all what it means in physics English. So in physics English, work has a really specific definition. In physics, work is when you apply a force to an object over a distance. So like if I push on something with 10 newtons of force for a meter, then I'd have an amount of work done of 10 newtons multiplied by 1 meter. So it's like a really hyper-specific definition for what work is. It's not just applying a push or a pull to something, not just applying a force, but applying a force over a distance. If I push super hard on the wall and I don't make that wall budge, doesn't matter if I push with thousands of newtons of force. If I don't make that object move, I've done zero work. Right? So work is the application of a force.
Should we write this down?
Yeah,
It's okay if we write it on a separate piece of paper.
that's fine. Or like the back side of this piece of paper if you want to. Over a distance.
Work.
So if I want a formula for this, a mathematical formula for this, I could say capital W stands for work equals capital F for force multiplied by the distance, or how hard I push, multiplied by how far I actually successfully move it. So, when you do work on something, you're like putting energy into it. If I do work on a baseball, as I apply a force to it while swinging my bat, I give that baseball energy. So if I apply a force over a distance to that ball, I might make it accelerate and have a velocity, and then I've got matter in motion, so that baseball now has kinetic energy. Yes?
Like, if you hit a baseball, actually, like, when you're hitting it, before you you're already always accelerating it, but, don't you make it slow down first, and then you make it go the other way?
You absolutely do, and you're completely correct in noticing, oh, the whole thing is acceleration. So it's coming towards you fast. First you have to make it slow down, and then you're changing the direction and then making it speed up, but speeding up, slowing down, changing direction. We know that all three of those are examples of acceleration, so very nice connection. And yeah, one of the fun things about this, we're going to talk about potential and kinetic energy. find there's a huge number of scenarios that you could explain using like Newton's 3 laws of motion, or you could explain using potential energy and kinetic energy. And either approach you take, you'll end up with the exact same answers, which is like really fun. You can take the same problem and solve it through 2 completely different routes and end up with the exact same answers. But this is what work is. So energy is the ability to do work. Now imagine I have a box and I lift that box up. I hold it up over my head. Okay? Now in order to do that, I have to do work on that box, because I have to apply a force to it. I've got to overcome the box's weight, right? And then I have to do that over a distance. So if I lift something up high, I am doing work on it. And through that action of doing work on it, I'm actually storing energy in that object. Because if I'm holding this box up high and I let go, what's it going to do?
Drop.
It's going to fall. And then it will have kinetic energy. Is this in frame, by the way?
Yes.
Great. Yes.
Also, I have a question. Like, I know some, like, when you go uphill, you go back down, you'll have, like, energy in your bike. But what happens if you're already on something, you're flat, and then you go down instead of going up and then down?
Okay. So I'm going to break this down because I'm not sure I followed that question exactly. When you, like, let's say I bike up to the top of the hill. If I bike up to the top of the hill, I am doing work. And as I'm doing work, I'm building up a store of energy. So I'm building up a type of potential energy. So this is another one of our types of potential energy. You asked me what the other ones are. The next one I want to talk about is gravitational potential energy. And that's when something has energy because it's up high. Right? Because if I have, a box that I've lifted up, if I let go, it's going to fall. If I'm on a bike at the top of the hill, if I take my hands off the brake, I'm going to start accelerating downwards. Right? So you have kinetic energy if you have an object that's up high. Anytime an object is up high, it's going to have kinetic energy. It's going to have gravitational potential energy. Because it could turn that gravitational potential energy into kinetic energy. Anything that's up high has the ability to fall down, and therefore accelerate, have velocity, be matter in motion, have kinetic energy. So the first part of your question was about that, and then can you repeat the second part? If you have an object that's like...
Oh, like, if instead of, like, the pencil's here, but I didn't, well, I put it there a while ago, but, if it falls off the table, even though I didn't just lift it up, how is this stored energy?
It has stored energy because it has a weight and it's up off the ground, right? At some point in the past, it made its way up high, right? So long as there's, something below it, if that table is no longer beneath it, if we don't have that normal force pushing up, now it's got the capacity to fall. And so it has gravitational potential energy because at some point it got placed there, right? Somebody put in the work to get that pencil to that location. So it definitely has gravitational potential energy. It doesn't have to be sitting on a slope. It can just be up high. So you can be on a plateau and you have gravitational potential energy because you could always walk to the edge of that plateau and, base jump off or something. All right, so anytime you're up high, you've got gravitational potential energy. The higher up you are, the more gravitational potential energy you have. The more you weigh, the more gravitational potential energy you have, because it took more energy to get you up high if you weigh more. How are you feeling so far?
Pretty good.
All right, do we want to cover more types of stored energy? All right, so we have chemical potential energy, we have gravitational potential energy. We talked about kinetic energy, electricity. How do we store electricity?
Like,
Valerie?
In batteries.
In batteries, right? So when you have electrical energy that's stored, now that's electrical potential energy.
But we already have electricity.
Yeah, so electricity would be like if it's actively flowing. Electrical potential is just, it has the ability to turn into electricity.
how do you put energy in a battery?
So later on this year, you're going to have a project where you're going to be making a piece of art that lights up using surface mount LEDs and copper tape and batteries. And we'll talk about how batteries work then. But basically a battery has two sides. And it's like there's one side that you've sort of crammed all the electrons into, and the other side doesn't have enough electrons. And given the option, the electrons will move from the place where there's too much to the place where there's not enough. But most of the time, there's no path to follow. So
it's like it has to jump.
yeah, so right, it can't just, manifest over there suddenly. But if you give it a path, if you create a circuit, a pathway of conductive material, then the electrons can flow from the place that there's too many to the place where there's not enough. So it's got electrical potential. It could become electricity given the option. Just like if I lift something up high, it could fall if given the option. So we've got electrical potential energy, and then the last form here is going to be the one that for y'all is actually going to be most important, because you're going to use this in your mousetrap cars. We call it elastic potential energy. And this is going to come into play anytime you have like springs or rubber bands or like objects that want to be in a specific shape. So like springs, rubber bands, hair elastics, anything that's kind of springy. So for example, here I have a hair elastic. This is the shape it wants to be in. But I could move it out of that shape by applying a force to it over a distance. So I do work on this object to give it energy. And now that I've given this object energy, I've stored that energy in it. Who's okay with me shooting a...
Me.
All right. So if I shoot this at Asa and miss, go straight over the head, that stored potential energy, that stored elastic potential energy, turns into kinetic energy. It's all right. It's just a hair tap. You're the last pass of the day. I don't need to shoot it again. So we've got elastic potential energy. So in your mousetrap cars, you are going to have a single mousetrap spring. And there's a certain amount of energy you can store in that mousetrap string by bending it out of position. Given the opportunity, it wants to slam back down into its original position. And your job is going to be to harness that energy to turn it from elastic potential energy into kinetic energy to make your mousetrap car be a piece of matter that's in motion. Make sense? All right. So we've covered heat, light, kinetic energy, electricity. Other ones that will come up, sound is energy. Technically, sound is also kinetic energy because a sound wave is just vibrations in air. All right, so we have all these different kinds of energy. We've talked about what energy is. We've talked about what work is. The thing that we care about is that energy can be turned from any one of these things into any of the others. So we spend a lot of time thinking about energy transformations. Energy being converted from one thing into another. Now, as this happens, there is a really important law that governs this. In the same way that Newton's 3 laws are laws that explain how the universe works, this is a law that explains fundamentally how the universe works. It is called the law of conservation of energy, and you should for sure write this down in your notes. So the law of conservation of energy says energy is never created or destroyed. It only changes form. Now, I am going to put a little asterisk next to never, because we'll come back to that. There is actually an exception to this law. There's sort of one circumstance under which this law can be broken. We'll get to that later. But broadly speaking, energy is never created or destroyed. It only changes form. And all of these different types of energy can transform into others. So let's take your horsey. This piece of this beautiful example of matter in motion. Imagine in your mind's eye a majestic horse galloping across the plains. Where does the horse have the energy to gallop from?
Food?
It's food, right? So a galloping horse has kinetic energy, it's matter in motion, but it got that energy from its food, which is chemical potential energy.
Ew.
So let's say you're feeding this horse, I don't know, this horse is getting the finest sugar cubes and apples. It's a spoiled horse, right? Where do the apples and cane sugar get their energy from? Calliope?
Would it be for plants photosynthesis?
Photosynthesis. We get some of the materials from the soil and from the air, actually. The raw materials, the carbon dioxide comes out of the air. We get some micronutrients from the soil. We get the nitrogen we need from the soil. But the actual energy to build these sugar molecules comes from light, photosynthesis, right? Photo means light, synthesis means to build. So then, they're getting their energy from light. Where'd the light come from? Asa?
The sun?
The sun! All right, so the sun is spinning out energy, and we tend to observe that energy in the form of heat or light. But the sun creates this energy through a process called nuclear fusion. And this is our one exception to the rule.
Oh,
Because what's going on in the hearts of stars is there are tiny atoms, hydrogen, the smallest possible atom, and they are being fused together. We literally smush together two hydrogen atoms, and from them we build a bigger atom called helium. And the weird thing about this process is that if you measure the mass of two hydrogen atoms, and then you measure the mass of the one helium atom that they turn into, the helium atom has a mass that's ever so slightly less than the two hydrogen atoms. An itty bit of matter literally disappears. It goes away. It is transformed into energy. Has anyone ever heard the equation E equals mc squared?
yes.
All right, I'm going to explain. I'm not going to make you use this equation in my class, but I am going to explain what it means. E equals mc squared. All right, so m stands for mass. Right, so this is that tiny bit of matter that's disappearing. What do you think E stands for? Energy. And C stands for the speed of light. And the important thing to note about the speed of light is it's a really, really, really big number.
Yes.
So if you take a really big number and you square it, you get an absolutely huge number. Right? A big number multiplied by itself is a massive number. So what this equation basically means is that through nuclear fusion or nuclear fission, which is basically when you have a big atom that breaks down into smaller atoms, but also has a tiny bit of matter go missing, when that happens, you can turn just a tiny bit of matter into a really big amount of energy. Make sense so far? So this isn't... Alim's like, no, this does not make sense. You're just telling me that this magically happens. Yeah, so here's a weird fundamental truth about the universe. Matter and energy are kind of sort of the same thing. And under certain really hyper-specific circumstances, energy can be turned into, or matter can be turned into energy. But really, energy and matter are the same thing.
How do you know?
And nuclear reactions, like what happens in the heart of the sun, or in nuclear power plants, literally break this law and turn matter into energy. So that's the only way to create new energy. Now, just about any form of energy that you will experience in your life, you can trace back to the sun. There's a handful of exceptions. If you're getting like geothermal energy, then that's not traced back. You can't trace that back to our sun. Does anyone here know where like your house gets your electricity from, or like what kind of power plant you've got, Valerie?
We have solar.
You've got solar, right? So there you're getting your energy really directly from the sun, right? You're taking light energy and turning it into stored electrical energy and then using that to run everything. Where else do we get our energy from?
Oh, isn't there a power plant like close to the school? It's like a really
Yeah, it's right over there.
Yeah, it's like a lot of.
Does anyone? I actually don't know. Does anyone know what kind of power plant it is?
It's electric. Yeah.
Yeah.
Well, most power plants are going to turn something into electricity. The question is like, what are you turning into it? Are you turning? All right. So let's say we got a gas-fired power plant. Okay. Gas is a chemical, and that chemical stores energy. We can release that energy by setting it on fire. Fire is literally just the energy that's released, right, when you have these chemical reactions taking place. Fire is the heat, the light that's being released from this stored chemical energy. So we take that gas, we burn the gas, we release the energy in the form of heat. We use that heat, so we went from chemical potential energy into heat energy. Now we take that heat, and we use that heat to boil some water. What does steam do? Like, where will steam go if you've got like a thing boiling?
Up?
Yeah, steam rises. So if you've got this matter that's now moving, what kind of energy do we have now when steam is boiling and rising up?
No kinetic.
That's kinetic energy. So you take this gas-fired power plant, you burn the gas, you boil some water, the steam rises. In the way of that steam, you put something called a turbine, which is basically just a thing that can be pushed on to make it spin. And the steam, as it moves through that turbine, pushes on it, starts it spinning. So now you've got a spinning turbine. That's a different form of kinetic energy. And attached to that turbine, at its core, are a bunch of really powerful magnets. And those magnets spin around some wires. Fun fact about electrons. Electrons can be pulled on by magnets. And when you spin magnets around a wire, you can literally yank the electrons through them. And that creates a flow of electrons. What do we call a flow of electrons through a wire?
Electricity.
That's electricity.
Oh my.
So the way a gas-powered power plant works is literally chemical potential energy into heat, into kinetic energy, into a different kinetic energy, into electricity. But where did that gas come from? Does anyone know where gas comes from?
Fossil? Oh no, that's oil. That's
Fossil
oil.
fuels in the ground.
We call them fossil fuels, and they're in the ground.
Bones. Fossils.
Yeah, so little creatures that used to be alive, right? This is, oftentimes they're like tiny single-celled organisms. I know we tend to think of it as like dinosaur bones. It's not really dinosaur bones, but it's like
Dog bones?
itty-bitty single-celled organisms made that using photosynthesis,
Like
right? So ultimately, the energy in a gallon of gasoline came from the sun. Just like the energy that our magnificent horsey is using to gallop can be traced back to the sun.
All energy comes from the
Because
sun.
energy isn't created or destroyed, it only changes form, with this one special exception, which is nuclear energy. I'll add nuclear to our list over here. Nuclear. Fission.
Okay. Well, now I have a question.
Yeah.
So you said everything will be traced back to the sun, right?
Yes.
So-
well, almost everything. There's a handful of exceptions.
Like what?
So geothermal.
What is that?
So like energy that's so like you know how the Earth has like
Yeah.
all these different layers, and then at the very middle it's real hot.
Mm.
So that heat is like leftover heat from when our planet formed. So that's from like way back in the past that just like hasn't cooled off yet,
Oh.
right? So that heat isn't from our sun.
Okay, like so let's say you have your blinds closed in your room and you're like doing activity like going on like a Peloton bike
Mm-hmm.
or like playing a game or something and you're using your energy, I guess. So how is it traced back to the sun?
All right. So you're riding your Peloton. So you've got kinetic energy, right? Because you're moving.
Mm.
That energy comes from your food, which is chemical potential energy. Let's say you ate a steak, right? That cow got its energy from eating the grass. The grass got its energy from the sun. So your energy traces directly back to the sun.
So it went back to like 1985.
There are a handful of things that don't trace back to solar. One of them would be something like nuclear power plants don't rely on the sun, right? Because then you've got these rocks, and like basically it's just like this uranium metal that is breaking down and releasing and turning a tiny bit of matter into energy.
Yep.
All right, we will continue this discussion tomorrow. Any last questions before we go? NuCl. It's nuclear, not nuclear. So fission is when you have a big atom that breaks down. Fusion is when you have small atoms that come together. In either case, we are taking a small amount of matter is turning into energy. All right, folks.
Thank you.
Check it out.